Okay, so let's talk through challenge problem from CC5. I know quite a few of you had questions on this. So here what we have is we have 4.56 grams of a mixture of ammonium chloride and calcium chloride dissolved in 100 grams of water, starting at 25 degrees, 0.2 degrees Celsius. After it's all dissolved, so that means all of our reactions are done, the solution was at 30.53 degrees Celsius. How many grams of calcium chloride were in the original mixture of 4.56 grams? So here what we know is that our total mass, right, this 4.56 grams, is the sum of both of them, right? So if we say our 4.56 grams is going to be equal to the mass of our calcium chloride and the mass of our ammonium chloride. Now the mixture of these two cause our temperature to increase. So kind of looking at these two, this is exothermic. That's going to cause the temperature to increase for our solution, which is our surroundings, because heat's being released into the solution. This is endothermic, which is going to cause our temperature to decrease for our solution. Now the balance of these two is going to tell us overall we must have a greater contribution to our temperature change by calcium chloride, because overall our temperature increased here. So now let's break this down into our heat transfer. So if we have something happening, our reaction causing something else to change temperature, our solution, we would start with this, right? Q1 equals negative Q2. Now once we're looking at this, we want to say, can we quantify these two? So if we have a reaction occurring, this is not from a temperature change causing heat to be transferred. This is from a difference in potential energy. Okay, and the way we quantify that is either Q equals delta H or Q equals delta E. Okay, so this would be at constant volume, this would be at constant pressure. We're in a calorimeter, so we're not in a bomb calorimeter, so we're not having constant volume. So if we're going to quantify our heat exchange, we would use our enthalpy. And then if we're looking at our solution is undergoing a temperature change, meaning we can quantify the heat exchanged as either Q equals C delta T or Q equals ms delta T. Well, we know that our temperature change is provided. The mass of our solution total, which is going to be our 4.56 grams of solution plus 100 grams of our water, sorry, the 4.56 grams of our salt. And then the specific heat of our solution is going to be equal to the specific heat of water, which is going to be 4.184 joules per gram degrees Celsius. Right, and this is something that we've discussed in class, that since it's mostly water, we can make the conclusion that the specific heat is equal to the specific heat of water. So now we have a way of how we're going to quantify our solution heat and how we're going to quantify our reaction heat. And so we go and think, what do we have all the information for? We have all the information for our solution. We have the mass, specific heat, and temperature change. So let's go ahead and quantify that. Okay, so the heat of our solution is going to be equal to the mass of our solution, specific heat of our solution, temperature change of our solution. And so that's going to be equal to our 100 grams plus the mass of the salt that we added in, which is our 4.56 grams, and we have our specific heat. We have our temperature change, so we started at or ended at 30.53 degrees Celsius. We started at 25.20 degrees Celsius, so this temperature change is going to end up being 5.33 degrees Celsius. So the amount of heat that was gained by our solution, and we know it's gained because it's increasing, is 2,330 joules. Now, how does this relate to our reaction? Because our reaction depends on our enthalpy. And our enthalpies up here, we know, are provided for a mole of calcium chloride giving us 82.9 kilojoules released, a mole of ammonium chloride giving us 14.6 kilojoules of energy absorbed. Okay, so now we know that the Q of our solution is equal to the opposite of our reaction. So that would tell us the amount of heat lost by our reaction is negative 2,330 joules. Now, if we go back up here, we see our units. So we got to keep pay attention to our units. Our units for heat here for our enthalpies is kilojoules. So before we mess that up, let's go ahead and convert that to kilojoules. So we divide by 1,000, we get negative 2.330 kilojoules is equal to our reaction heat. Now, normally this would only correspond to one reaction. Okay, but we have two reactions here. We actually have two concurrent reactions occurring. So that would mean the Q of my reaction now is equal to whatever reaction occurs with my calcium chloride plus whatever reaction occurs with my ammonium chloride, because we have a mixture of both of these. Well, if we're going to quantify each of these, we could say the Q of my calcium chloride is equal to the enthalpy change of my calcium chloride times the number of moles of calcium chloride reacted. Similarly, we can say for my ammonium chloride, the heat exchange there is equal to the enthalpy change when we dissolve our ammonium chloride times the number of moles of ammonium chloride. Now, why am I adding in this molar amount for each of these? Because if we go back up to our reaction, we're provided information for 1 mole of calcium chloride dissolving and 1 mole of ammonium chloride dissolving. So now let's see what information do we know about each of those. So over here we can see the Q of my calcium chloride is going to be equal to the enthalpy change for my calcium chloride, which is negative 82.9 kilojoules for every mole of calcium chloride. And that would be times the number of moles. Okay, but our goal here is to quantify the mass. So let's go ahead and put in here, instead of moles, the mass of calcium chloride divided by the molar mass of calcium chloride, which is equal to the number of moles of calcium chloride. So that's just using our molar mass conversion factor there. So we can say now the Q of our calcium chloride is negative 82.9 kilojoules per mole of calcium chloride times the number of moles, which is going to be X. I'm going to call our mass of calcium chloride, and the molar mass 110.98 grams per mole of calcium chloride. So now we see we have a per mole and a mole, and so that cancels out. And so if we go ahead and get a number for this, because we're going to use that, if I go ahead and multiply across 82.9 times X divided by 110.98, I'm going to get negative 0.747X, right? And remember, we defined X as the mass of calcium chloride. Okay, so now we have an expression for calcium chloride. We can do something similar for our ammonium chloride. So the heat of our ammonium chloride is going to relate to the enthalpy change of our ammonium chloride times the number of moles of our ammonium chloride. So we do something similar here, and we say, well, the enthalpy change for our ammonium chloride is 14.6 kilojoules per mole times the number of moles of our ammonium chloride. And again, we can do this as mass of ammonium chloride divided by the molar mass of our ammonium chloride. So now we can get it into mass, right? Because we're dealing with the mass here. Now, before we do that, what we know, right, is that the sum of our two masses. So if we go back up here, the sum of our two masses is equal to 4.56. Now, I only want one variable I want to solve for. So if I called this X, I can define from there the mass of my ammonium chloride as being equal to 4.56 minus X. So that way now we only have one unknown variable. So if we go back down here, we're going to see that our enthalpy change now, our heat for ammonium chloride, the reaction there is going to be equal to our 14.6 kilojoules per mole of ammonium chloride times our moles. Now again, we made this into mass divided by molar mass. And we said that's 4.56 grams minus X, because we defined X as the mass of our calcium chloride. And if the sum of those two is 4.56 for our mixture, and then the molar mass is 53.491 grams per mole. So now again, our moles cancel out, and if we go ahead and expand this, just because we're going to use it in the next step, so we're going to multiply across here and then divide by our 53.491, we're going to get 1.24 minus 0.273x. So now we have an expression for how we've defined the heat of our calcium chloride and the heat of our ammonium chloride with respect to the mass x of our calcium chloride. So now if we just go ahead and scroll up here and go back to how we defined our total reaction heat, calcium chloride plus the heat for the ammonium chloride reaction, now the total of these two is going to be equal to our Q of our reaction. So now we get Q of calcium chloride plus the Q of our ammonium chloride reaction, so that's going to be negative 0.747x plus 1.24 minus 0.273x. And we already defined and calculated what the Q of our reaction is. We already found that it is negative 2.33 kilojoules. So now I'm going to go ahead and combine like terms here. Okay, so I'm going to get negative 2.33 kilojoules equals our combined terms that we have for our reaction. So we're going to get negative 1.02x. So I just combine the terms with x here. I'm showing the step-by-steps of our algebra here. Minus 1.24x. Okay. Excuse me. Plus 1.24x that we're dealing with here. And so now we can go ahead. Oh, there's no x here. It's just 1.24 from our 1.24. And so now we can go ahead and add in our 1.02x. And so we're going to get our 1.24 equals our negative 2.33 plus our 1.02. And so we're going to get, oops, negative 1.31 equals x. Excuse me. Oh, I'm combining the wrong terms here. We always make mistakes. It's okay. So what we're going to do is we're going to subtract 1.24, subtract 1.24, and so we're going to get negative 1.02x equals our negative 3.57 kilojoules. And so we divide by our x, okay, and so we get x is going to be in, divide by our negative 1.02, and so we get x is going to be 3.50 grams, because that's we define that as the mass of our calcium chloride. So now we defined the mass of our calcium chloride. If we wanted to find the mass of our ammonium chloride, we would take our total mass, subtract the piece that is our calcium chloride, and we end up getting 1.06 grams of ammonium chloride as well. So now we're able to define the mass of this mixture, right? So this was a lot of different pieces here. So if you want to take the time to kind of think through this again, we have a mixture where we have an exothermic and an endothermic reaction occurring. The sum of our masses is 4.56 grams. Some amount of that is going to cause our temperature to decrease. Some amount of it's going to cause it to increase. And so we were able to find the heat of our solution here by going ahead and identifying, we knew the mass of our solution, the specific heat, and the change in temperature. So then once we found the heat of our solution, we know that's equal and opposite to the heat of our reaction. So we found the heat of our reaction. And then just to save a conversion step, maybe mistake later on, we noticed that our enthalpies are in kilojoules, so we converted that to kilojoules. Now again, we realize that there's two reactions. So this total amount of heat came from